Good morning, everybody. Good morning. So, I hope you're in the right room. This is Geo322. Surface processes. Everybody good with that? Yeah. I mean, if you're not here for that, you're welcome to stay. But, got my phone there. I'm going to experiment with taking video of my lectures and perhaps posting those. Never done that before, but so we'll see. It might be too excruciating for me to watch myself if I have to review these things. Anyway, let me start with just the very basics. I think all of you got a copy of the abridged syllabus over there. Pardon me while I try to wake up my voice a little bit. There is a longer version that you are also responsible for, right? You know, because the syllabus often contains all the various policies and so on. But this is the, if you go to home on the Surface Processes Geo322 site on Canvas, it will take you to this syllabus page, which has a version of the abridged stuff on there, but also links to the full syllabus and links to that abridged syllabus that I printed out for you. The Canvas site is also where you will get weekly take-home quizzes. There will not be one this weekend, that would be silly. But most weekends thereafter, I think there are 8 of those. And those will be posted and available on Friday afternoon and due in class Monday morning. So I know the whole homework over the weekend thing is a bit of a drag, but I don't expect them to take you all that long. You probably bang them out on Friday afternoon if you're diligent about that. Those are going to be graded. I've only been doing these for a couple of years, but what I found when I just didn't grade them, because I figured I really just wanted to incentivize people to actually look at the material and do the work, but people didn't kind of, without comments in there as to whether no, this is wrong kind of thing, it's easy for people to read the key into their own answers and vice versa, or however that works. So I will be grading those for credit, usually not terribly harshly or anything, but we're trying to figure out, you know, how we're doing in terms of getting you the information, and also preparing you for the exams, because the exams will generally, the exams will come from the quizzes. Not necessarily all verbatim, not necessarily exactly the same questions, sometimes based on how people do or do not do well on some of the quiz questions. I will make the exam questions perhaps a little less ridiculous. So, any questions on that before I move along? Right now I'm gonna, what I will say is that mostly I do not use PowerPoint. I find it counterproductive. And so I generally get Chalk Talks, and I'll put up slides when I need to, right? Graphs, photos, that kind of thing. It keeps me at a pace that's reasonable, because I'm not writing probably any faster than you can write, or at least not much in most cases. In some cases, perhaps you can write faster than I can. So it at least serves that purpose, and yeah. So, if there are no objections, I'm just going to plow ahead. I want to just sketch up a real bare bones outline of the course. Kind of move some furniture. All right, so we're going to cover what I think of. I think I can generally classify into something like 4 categories. One being weathering. That is the taking intact rock and breaking it into small pieces and chemically altering it also. The second, and this is in order of appearance in the course, glaciers. Glaciers have to come somewhere in the course, and they might as well come here. And so we'll talk about glaciers. They're pretty cool. I think that is kind of self-explanatory. Third, mass movement. And this is a bit of a catch-all term for including things like diffusive processes on hill slopes, even bioturbation, worms moving stuff around, to landslides and debris flows. Essentially, stuff that moves that is mostly earth rather than mostly water. And then we'll, as the fourth, we will do the flowing water, / streams, etc. So in general with flowing water, because some stuff that is mass movement looks a lot like flowing water. So there is a bit of a gray area, but essentially anything that is so dilute that the particles in the flow do not interact, or I can assume that they don't interact, that's a flowing water process. The particles are concentrated enough that they do interact, that's a mass movement, such as a debris flow or a hyperconcentrated flow or a landslide or what have you. Yeah?
Is the differentiation between those two based on like its Reynolds number?
No, more just based on the solids fraction. Flowing water, generally water that's moving a lot of sediment, even pretty turbid, muddy water, actual concentrations of sediment will be kind of surprisingly small. And since I don't know off the top of my head what sorts of concentrations those might be, I'm not going to throw those out there. But when we say mass movement, we're talking stuff where the solids fraction typically is larger than the liquid fraction. That's kind of what it takes actually to get to, typically to get to the sort of having particle-particle interactions as a routine feature of the motion and the dynamics. But sometimes there can be a bit of a fuzzy line between these two. So now, what I'm going to also do is say, well, that's our sort of topical areas, but I do want to cover some principles. And what I'm just going to sort of insert a topic 0 up here and call that principles. And spend most of today talking about that. So, there are simply themes that come up over and over again in this course, and I can give you a bit of a heads up on this nice introductory first day. Week 0, I'll call it item 0 on the menu here, and great. Have a drinking problem apparently. All right, so unless there are any objections, I will move forward with talking about some principles in service processes. Principles that, all right, so let's just dive right into it. I hate to do chalkboard maintenance, but I just know it's going to bug me and bug me and bug me. All right. So the first principle, the first sort of principles, I might just say tools. We might even call these general methods. Principles is just sort of a nice catch-all thing to put it in here. So let's start with force balance. I'd say that is the primary quantitative tool that we will use when we consider a lot of surface processes, particularly, well, when we're talking about how glaciers move, we do a force balance and we have what's known as a rheology. Now what is, anybody want to venture what rheology is? Kind of a fancy word. Kind of one of those words that I actually pretended to know what it meant for a long time until I finally really looked it up and got the definition and discovered, okay, rheology is the description of strain rate as a function of applied stress. This is essentially describing how things move when we push on them. Okay? So we might have, for example, a piece of earth on a tilty slope that's and the earth is wet, and we have that force of gravity tending to drag it downhill. We have its frictional resistance against some potential failure plane resisting that motion, and we want to do a force balance to see if it might move. Now, typically when we do force balances, we're actually going to go down to really stress balances because it's not too awfully often in geomorphology and surface processes that we can do sort of treat things like point masses. More often we've got gravitational field, we've got a hillside of earth, or we have a wide stream carrying things, potentially entraining gravel and other material at the bed and moving those along. So when it comes to actually doing the math in this class, there are a couple of things that I'm going to want you to be able to do. One is, for example, to make some sense of the force balance for landsliding, because those kill people, and also to make sense of the method by which we decide whether a grain, such as a piece of gravel or even a boulder, might be entrained, might be moved by flowing water. And that's pretty useful to do. It's just a really, if there's one thing, if you're not a surface processes type geomorphologist and you want to take one tool away from surface processes, often that sort of initiation of motion, like, well, how big is this boulder? Could it have gotten here by the kinds of flowing waters that I know about? It's a useful tool. I mean, it's essentially how people discovered that there were things like the Missoula floods and the Bonneville flood. Because there were these boulders that couldn't have been moved but for very big flows that were not, just could not happen under present, without some glacial dam break, some dam break flood type thing. So a lot of the time what we want to know is questions of whether something is going to move or not. So this go, no-go question will come up a few times. In particular, for example, with respect to landslides, in particular with respect to particles that might move on a bed. We just want to know, okay, if my rheology maybe looks something like this, and if I'm just, rheology means I can graph it, right? I've got strain rate versus applied stress. I can make a graph out of that. I can put strain rate on the vertical axis. And I can put applied stress on that horizontal axis. And we may have some number of processes that behave something like this. That there is what we would call a yield strength. That we have to attain before we get any detectable rate of motion whatsoever. I did kind of gloss over perhaps a fancy word. I mean, it's only one syllable and everything, and I think people understand strain and sometimes in a colloquial sense, but usually if you're talking to your friends about strain, you might really be talking about emotional strain or something along those lines. Strain is simply, there's actually a mathematical definition to it. It's a quantity between 0 and 1 that describes this sort of fraction of deformation of something. It's kind of a nice catch-all. It doesn't do so well as a concept once we're talking about stuff actually barreling downhill at 10 meters per second or something like that. That's typically where this arrow goes vertical at some point. But it's pretty handy in terms of thinking about a yield strength for, say, landsliding. So we might call this curve our landslide curve. Glaciers tend to do something like that, and we can approximate that process of glacial ice deformation with something like a yield strength, and you'll use that in one of your labs to actually reconstruct ice profiles from moraines. That's sort of a nifty exercise. So, whether it's actually a real threshold or just highly nonlinear, we often do have some highly nonlinear relationship between strain rate and applied stress. Not everything's sort of that kind of like, okay, I put force on it and it just bends smoothly, maybe linearly with the amount of stress I apply. Often when dealing with earth materials, soils, etc., what's going to be graphed up here might not necessarily be strain rate, but actually strain. And curiously, a lot of the old school graphs of this kind of thing actually have the axes flipped. They have applied stress on the y-axis and strain on the x-axis, and I find this horribly confusing. So I'm not going to do that to you because, I don't know, maybe it would make sense to you, maybe it's just me, but there's a decent chance that it's not just me. Okay, so one way to think about these opposing forces in geomorphology is how rapidly I can chunk this chalk. one, sort of whimsical way for me to conceptualize this sort of force balance stuff is that we have geomorphic agents. And now, let's see the agent man.
Heard rumors of this guy.
You heard about him? Yeah. Okay, so there's our geomorphic agent. He is, and he could be a she. She's he. He's taking action. Using whatever tools, perhaps a hammer, and he's taking action against some kind of earth material. And best I can sort of figure is, we'll have our earth material down here, sort of our half dome with our scree slope, and here's the rock here. When I did a year ago, I wanted to find a good secret agent cartoon, so search Google Images for agent, secret agent, spy, that kind of thing. And when I looked for images of a rock, cartoon images of a rock, I got Dwayne Johnson with his T-shirt that says "Just Bring It." So there we go. Our earth materials, they're resisting the agent's actions. With whatever is handy. Maybe it's the tensile strength of rock, maybe it's a frictional strength, but just for grins and giggles, I'll draw that in as a Captain America shield here. Alright, so resisting the actions of the now we can also have, so often we will sort of micro in on, okay, we've got this agent acting on this, we're trying to figure out if this rock can break, and how it might break and what might cause it to break, whether this particular slope might fail or not. And we'll zoom in pretty close on a particular force balance. But one of the things that we'll need to also think about is that we might have agents competing against one another. So, for example, if we've got gophers moving stuff on slopes, we have a stream at the base of that slope moving stuff away. If we suddenly crank up the rain rate, we might start gullying up into those slopes. We might start out-competing that flow action, that flowing water might start out-competing the gophers as geomorphic agents. This competition results in something like a balance of power that typically gives the landscape its texture. So again, if we have very powerful gophers and not so much power in the way of streams, then we might have very broad slopes, streams few and far between, a sort of coarse texture to the landscape in terms of its, what we call its drainage density. How many streams sort of per area do we have? What's the length of streams per area, for example? On the other hand, if the sorts of processes that are channelized by flowing water are really strong compared to those gophers or whatever else might be sort of gently diffusing stuff off of the slopes, then we might have a highly dissected texture to the landscape, lots of streams per square whatever. All right. Next principle, or wow, see, I told you I can chunk up this talk. Or I didn't tell you I could do it pretty quick, but I bet I can do it pretty quickly. Oh wait, that's not a... All right, so our number 2 in our principles, I'm going to call conservation of mass. And this is just bookkeeping for some control volume. What's a control volume? The control volume is wherever I want to draw an arbitrary shape around and keep track of what's coming in and out through the sides of that shape. Typically it's, so say I've got a surface here, might have some trees growing pleasantly enough, some grass and whatnot, and down here might start getting lots of big rocks, and then finally some intact bedrock down here. If I want to analyze that, then it might be a good idea, or one tool I have is to draw a box around it. Work in progress. You can draw a box around that, and you know what? Actually, I don't like that box. I don't need to make it square. I'm gonna draw it more like that, and I'm gonna pretend that this bedrock soil interface is a bright enough line that I can draw a line like that through it. I'm going to say, okay, I've got weathering, and I'm also going to move this with the slope. If the slope is degrading, if it's getting eroded, I'm just going to keep that box wrapped around that soil and move it along and say, okay, I might have some soil being transported in from upslope, I might have some soil moving out downslope, and then I've got some soil moving in via weathering at the base. And doing some really simple stuff with that kind of force balance, we can come up with pretty good mathematically, really just actual mathematically descriptive models of how slopes evolve and some idea of their shape and how we might interpret various aspects of that shape. And I'll talk a little bit about that towards the end. So for example, just this basic conservation type tool can tell us that the curvier the higher the curvature, the sharper my ridge top, the faster it's eroding. It's actually something you intuitively know. I mean, you know that if you build a ridge top out of sand or mud or something and you make it very sharp and then you start dumping water on it, that really sharp bit's going to erode away pretty quickly. But we can put the math to it, and you know, that can be useful. We'll use that control volume, that conservation of mass principle, often enough. You know, and sometimes we might just think of it as, well, okay, I've got my agent here. and say he's got a shovel. He's got stuff on that shovel and he's filling a bucket. And we can conceptualize what's going on in terms of, okay, here's our control volume, how much stuff is in that bucket. We've got maybe an agent filling it, we might have another agent emptying it. We might have 2 or 3 agents filling it, whatever. But we can think of these various actors in this sense. If we want to think of this soil column as our bucket, we just keep track of how much is in the bucket, you know. And again, we can apply some pretty simple rules and do pretty well with that. Now, another one that'll come up a little bit, maybe not all that much, but as long as we're throwing out conservation principles, we can sometimes use conservation of energy to get somewhere. Particularly in the case of, say, water flowing downhill. I know it's losing potential energy at some rate because I can measure its velocity. And I therefore know how much potential energy there is to turn into some kind of kinetic energy and how much energy I've got to maybe do work on particles that are on the bed in terms of transporting those. So conservation of energy is often a way of formalizing the good old principle of what goes up must come down. And what goes up further comes down faster and or does more work on its way down. So, all right. Let's see, number 4. Number 4, 1 through 3 are, in my mind, mostly physics, also chemistry. I mean, I sometimes forget the fact that in order to get rock into soil, we often have to have some chemical reactions. We've got some flux of ions, in particular, out of here, either out the bottom or up into the tree roots. And those are affecting the properties, you know, essentially how strong this shield is. We think of the old school Captain America before vibranium. You know, his shield had to be recoated now and again, and you know there was drama in Captain America when the coating got particularly thin. If you want to think of it that way. Chemical reactions are doing stuff along those lines. So we've got chemistry and physics here with numbers 1, 2, and 3. Frequency and magnitude is more about statistics. And this is just how often do events of different sizes occur? And what are the implications of that for what moves at what rate and how often? You know, we know, for example, that big floods are amazing at moving lots of stuff, but the biggest floods happen very rarely. And so what about the relative contributions, say, to overall sediment yield from those biggest floods versus ones that are big enough to move some stuff, just not as fast as those biggest ones? You know, how do we think about the effectiveness, what we actually term the geomorphic effectiveness of different sorts of events, of different magnitudes and rates of occurrence. And this particularly comes in when we're talking about floods. You know, on a gravel bed river like the Willamette, it kind of pretty much takes a flood to move the bed. gravel bed rivers, the gravel may only move a few hours a year, if that. And so is it what moves more of the gravel? Is it the events that do occur every year and move a bit of gravel, or is it those ones that occur every 100 years and move lots of gravel? Do they actually move 100 times as much gravel as the yearly ones? And we won't dive too deeply into this. It's more just, keep this one in mind, because the way it looks now, as natural as it looks, as much as it looks like it's always like this way, it isn't always like this right now. That river is sometimes raging. It's not always a calm little thing that you want to wade through. Yeah.
How does that change with anthropogenic influence such as dams?
Oh, it really mucks things up. The people, it's like looking at any flood record from the East Coast is just hopeless. Because the rate of urbanization, the rate of increase in impermeable area makes, I recall when I was in graduate school, the general case that was sort of brought up was, okay, these culverts on these highways were designed to transmit the 50-year event, but they're overflowing every year now, and it's only been 10 years. Or whatever it was. So, yeah, that's a big deal. Also, of course, we've got just anthropogenic effects on overall climate, which make things a bit squirrely there. When you're looking at flood records on a lot of rivers, you also have to consider dams. If I want to say something about how often stuff moves in the Willamette, it'd be kind of a mistake to look at the record before 1972, I think it is, when the last dam was closed. So, yeah, that's a big thing in the statistics. There are tools that we can look at some of these records and try to determine whether they're what we call stationary, that is variable, but the mean is constant. Or not. It's all those sorts of statements come with some degree of confidence and not so confidence. The final thing that I want to talk about is because, number 5, I'm going to call reading the landscape. And we might say reading the landscape. We might also acknowledge that we might be looking at smaller features. We might be focusing in we might be looking at an overall landscape from an airplane or a drone, or we might be pulling up to a road cut and looking at what's going on there. And I'll show you some examples in a few minutes of looking at different scales. But we're going to be, when we say reading, well, where are we reading from? We might be on the ground. Looking at the surface, or even looking at soil horizons. We might also, or instead, be looking at topo maps. The 7.5-minute quadrangles, the ones with the brown contours on them. Nowadays, we would often want to look, and we'd be, if we were being paid to do this sort of reading, it would behoove us to look at LiDAR, or try to get some LiDAR coverage of our particular area, because it just shows so much more than we see in the topo maps. So I'll share just a little story with you. We were doing a bunch of analyses at some point of topography in the Oregon Coast Range. This is back in the late 90s. And there seemed to be this absolutely dead north-south fault line that separated, like, higher drainage density or more, sharper bits in the landscape versus smoother bits in the landscape. We started looking at the maps, and it was clear that simply different people had drawn them based on the aerial photographs. One person had just drawn in, been a lot more, obsessive compulsive about drawing in all the little sharp bits, and the other person not so much. And it was blew our minds sort of, but it was on the other hand, it was like, well, kind of duh. We knew that the maps were hand drawn. We just hadn't really hit home like that. Our other tool is aerial photos. Sometimes those are satellite, but typically we prefer some lower altitude shots to get aerial photos of a land surface, unless we're looking at a really big feature, then the satellites might be just fine. So what are we doing? In terms of reading the landscape, we're looking for evidence of these process actions and the relative rates, either say between different processes in the same area or similar process suites between different areas. Probably best at this point in terms of illustrating a bit of landscape reading is to actually look at some pictures of some landscapes. And show you what I mean. All right, let me fill a bit of light here. So in the first 10 days of September, I went to Scotland. I almost said it like Scotland. If you, I found that if I didn't mimic them, I was misunderstood. I tried ordering fish and chips. I tried ordering cod, and that, had such a hard time with that being the same word as cod. That she was like, paddock? So here we've got the, I'll remind myself, this is the river Elfeg, one of those unpronounceable Scottish names, near the Falls of Glommoch. And so here we've got running water. This river starts in a loch a little bit upstream of here. We've got running water. What's that water doing? It's creating, if you want to think of it as a geomorphic agent, well, it's generating shear stress against the boundaries of that channel. And in particular, we can see where, it's probably not doing much now. This brown tint to the water is actually a tint. It is stained brown. It's not really carrying mud at this point, I don't think, although it was raining kind of hard at some point in this day, but rains a lot in September in the Highlands. But here's what I keyed into, and I didn't even see this at the time, partly because the weather was so miserable, but notice these big blocks that are either not ripped out of place or ripped out of place but not moved very far, perhaps. And what this is telling me is that, sometimes this, I don't know how often, but this river gets flowing fast enough to generate enough shear stress to move some pretty big pieces. And I can also see that I don't see smoothing, grooves, potholes, those sorts of features on any of that rock. So I would surmise then that the rate at which it can move out the rock via plucking out big blocks is substantially way faster than the rate at which it can erode the rock via, chipping away at it with little sand and gravel grains. So that's an example of of my reading of that part of the landscape, even if I didn't do a particularly good job except to see, oh, what a pretty waterfall when I was actually on my hike. Here's a good one. This is, okay, let's try to pronounce the name. This is Fiona Corey. Got to burr the R. With Loch Fiona Corey right there on the side of Blaven in the Black Cúden. You don't actually hear people pronounce these things. It's like, I don't know, could be almost anything. So, what might I be particularly interested in here? Well, one of the things about Scotland is these amazing glacially carved valleys, and particularly these huge glens, like the Grand Glen in which Loch Ness sits, that completely straddle the island and are faults. And so the ice got into these faults, and I'm surmising that fault breccia near that fault was just more erodible enough that it got preferentially eroded and carved out these amazing glens. But you've got these sort of relic glacial features all over the place, including, you can see here, this U-shaped valley, and it looks like, especially when you look at the contours, like there was ice flow over out that way. Well, right now there's a little over deepening right here, sort of. It's common to find ponds in cirques where you get that over deepening near the head of the glacier. But look here, we've got this really steep-sided canyon notching up into this Goyde, or what normal people would call a cirque. And it's really, it's buzzing down. I don't, so I go, well, I can't help but, be the geek and go, how fast does this happen, right? Did this all happen in like the first 1,000 years after deglaciation, and it's just been kind of sitting there ever since, or first 100 years? I mean, I don't know, or has it been progressively working its way down over 10,000 years? Given the number of waterfalls that you can't see in this photo, but I know are on that stream, it's likely that those kind of move as nick points up through the system. So, yeah, that's a thing. Now, in the foreground, even we've got so this is an example where over the course of the Pleistocene, we've got glaciers carving out these valleys, and then in between glaciations, we've got streams doing their business and bringing that bedrock down, but doing a much more focused job of it. That's an interesting process competition. It seems that over, say, Pleistocene timescales, glaciers are winning, but the streams are certainly having a say in things, at least in creating these little canyons. In the foreground, we've got lots of broken rock and even some rock that's not so broken. So we might be able to look at that more closely and think about or figure what might be the process, what are the potential weathering processes that are breaking up that rock. Although just looking at it right there, I wouldn't want to, I'm not real prepared to say. Let's just say that. Here's something much closer to home. This is, I might have to sort of sketch this for you. Sometimes pictures that seem to make sense just look green. This is Chipross Park in Corvallis. We've got really steep hillsides coming up on either side of this little bottom of this ravine. And this, if you go to the top of Chipross Park, this is just one of those ravines that you could sort of stumble down into if you wanted. And this is a day or two after a really big storm, big by our standards. And I'll just wrap it up by saying we've got running water here. We've got gophers pushing out stuff here. We have some slurrying of the gopher mounds there. And so some process competition going on there, which I was awfully psyched to see because I've been taking students to this site like for years and going, I think maybe fluvial must be carving, streams must be carving down here, but we don't see any evidence of it. And I actually got pictures of like gravel on top of grass, so it doesn't even need to, because this is coming up over the top of the grass, we don't even need to cut down through the grass for the fluvial to keep up. All right. I will quit there instead of waxing philosophic and whatnot about more pictures. Next time, Monday, we'll dive right into weathering, mainly to start with chemical weathering as we rock the rock in preparation to breaking it to bits. So, yes?
Where does our field trip?
Our field trip will go here. It will also go to a nifty site to look at these two soil profiles in the Coast Range.
Nothing overnight.
Nothing overnight. Yep.
We're at the Coast Range.
At the headwaters of the North Fork Allsea, where you've got the piece of volcanic rock that's holding up the Allsea Falls and another falls stream of that, like pinning a bit of the landscape and creating this 1 meter thick soil that's red, like 100,000 years red. And then you move right around where neighboring streams are cutting into that sort of plateau almost. And you got
that's fine.
soil profile.
Yeah, that'd be
So that, pretty really cool kind of geomorph geek out kind of place.
Hi. So I'm going to GSA the first week of November. So I will totally miss the quiz. Will that be a huge problem?
Well, the quiz will take home. You can get those. You need to get those from somebody.
Okay. That shouldn't be a problem.
They're, since Veterans Day, they don't have a lab that week. The lab won't be due until the following Monday. So the lab from game level 1 will be due.
Okay, so I'll have that.
Yeah.
Okay.
Is that essentially what you need to do?
Yes.
Okay.
Yeah. Perfect.
The quiz that there will be assigned on Friday will be due on Wednesday, of course.
Okay.
Typically, I ask people to give me hard copies of those, but if you're going to be out of town, I'll let you send me a scan of it.
Okay. Yeah. All right. Great. Thank you.
You're welcome. Hey. Yeah, I heard that from somebody else too. So
I just want to make sure.